So it's my really great pleasure to introduce today's Thursday seminar speaker, our very own Jacob Fields. Jacob originally worked in GRB physics, is my understanding, in his honors thesis at Brigham Young, and then went to Penn State to work with David Riemann, who used to be a member here not too long ago, on numerical relativity. And today we get to hear a little bit about what he's been up to, or what he used to be up to before coming here, and specifically on improving neutron star mergers with advanced computational methods, presumably numerical relativity, among other things. So join me in welcoming Jacob and take it away.
Great. Thank you, and thankful for the invitation to speak. A little thing on the GRB thing, my undergraduate advisor was also a numerical relativist. So I was really just doing relativistic fluids and then asking people at Los Alamos, what does this mean, over and over and over. My actual interests are more in compact objects, which, GRBs do come from compact objects, but I like the objects themselves more. And so today I'm happy to talk a little bit about some of my work looking at kind of ways that we can make our computational methods better so that we can do finding neutron star measures that are more accurate and give us some more interesting physics. So I think probably everybody in here knows what a neutron star is, but I will still go over some of the life cycle details of a BNS merger just to make sure we're all on the same page. So the general idea is that you have this in spiral phase. You basically have two neutron stars that through some process have become gravitationally bound to one another. And because these objects are very compact, but still very massive, as they orbit one another, they emit gravitational waves, and those gravitational waves carry away energy and angular momentum, and that causes the orbit to shrink until they spiral in faster and faster, and then they eventually merge. During this merger phase, you can have basically three outcomes, more or less. The simplest outcome is that your neutron stars are very massive, and so as soon as they collide, they form a horizon, and everything just kind of falls into their horizon. This is called a prompt collapse. These are interesting in their own right for various reasons, but one of the things to kind of be aware of is that we don't really expect significant EM signatures from them. There is an asterisk here because there is some work that suggests, you might have something interesting, usually related to the idea that you have this magnetic field around a black hole. You have to get rid of the magnetic field somehow because of no-hair effects. But typically we don't really think of them as having significant EM signatures. The next alternative is you have a short-lived hypermassive neutron star. So this is, you have a remnant that for a very brief time is a neutron star that is significantly more massive than what the TOV limit allows. And so on relatively short timescales, it's subjective depending on who you ask, but we're talking, usually tens of milliseconds. These will collapse into a black hole. And then you can, have your usual black hole processes that can power something like a GRB, because you also have all this matter around it. And then you also can produce a kilonova. And then the other alternative is that you start with some relatively small neutron stars, and so you end up with a long-lived massive neutron star remnant. And long-lived here doesn't necessarily mean stable. It just means, it lives long enough that all of the interesting physics in the system happens before it collapses. And so this could be something that is permanently stable, but it could also be something that is, only stable for maybe a few hundred milliseconds, maybe a couple seconds. So I want all of you to care about neutron star mergers because I care about them. That means they're important, right? But some things that I think that they are very interesting objects, and they kind of reach into several different fields of physics. If you do gravitation and cosmology, the fact that they emit gravitational waves kind of makes them interesting in their own right. This is something that we pursued for a very, very long time, and then LIGO finally detected them, a few years ago. This also means that we can do kind of test for general relativity with them because we have some sort of way to measure what's going on in the system. And there are these, various tests of GR that everybody does with neutron star mergers and black hole mergers. And then kind of a fun little thing that you can do if you have, the stars align perfectly, is you can do independent measures of the Hubble constant, and that makes them very interesting to cosmology. If you work on nuclear physics, neutron stars are very interesting objects because the conditions are not really anything like what we can produce in a laboratory. You have something that is mostly neutrons, that is around saturation density. And it can range from being very, very cold to something that is, approaching 100 MeV in the merger phase. And so, you can kind of use them, use observations of these to put constraints on nuclear physics. And another way that also is done is through our process nucleosynthesis. So if you remember our colloquium last week, we heard a little bit about nucleosynthesis. Neutron star mergers produce kilonovae, and these are sites for our process nucleosynthesis. So you have these very, very neutron-rich nuclei that decay down toward the island of stability and produce a lot of heavy elements. And so this is kind of the one of the ways that we get a lot of the elements and some of their more isotopes in the universe. And then finally, if you do time domain astronomy, I've mentioned briefly a few times that there are these electromagnetic counterparts. And so if you are very interested in transients, you get short GRBs and you get kilonovae, and you possibly get some other things as well from looking at neutron star mergers. As you might imagine, because there's all of these different ways that all of the different physics that's interesting. There's a lot of kind of modeling complexity that goes into neutron star mergers. And if you want to do anything kind of ab initio, the only way to get all of that physics together and actually have the equations be solvable is to do it numerically. So this is where numerical relativity comes in. So first kind of component you need, first ingredient for your recipe is that you need to solve the Einstein equations because we have compact objects with strong gravity. And then your neutron stars, you can think of them to a very good approximation as perfect fluids. So something that doesn't have any sort of shear viscosity, at least on the timescales that we're interested in. And that means that you can model them with hydrodynamics. But they also have very strong magnetic fields, and they're essentially very close to superconductors. And so you need to make sure that your kind of fluid treatment also incorporates your magnetic field effects in there. And then your next components, you need to think about all of these different nuclear things that you need. And so you have to have a realistic equation of state that incorporates nuclear effects. This is going to be something very different from an ideal gas. You have very neutron-rich material that will decay, and you have all of these other weak interactions that will go on when you go into the high temperature regime. And so neutrino radiation becomes very important. And then finally, especially if you're looking at kind of the later stages, when you're looking at your kilonova and possible light curves and predicting the what the spectrum will look like, you need to think about nuclear reactions, and so you need some sort of nuclear burning probably in these stages. And so you naively would say, okay, well, let's stick all of this on a computer and we'll just do all of it. But you need to take into account that there are physics uncertainties. Basically, all of these have very significant uncertainties attached to them. And then you need to take into account that you have finite computational power, and the end result is that you will not like it at all. You will be very sad if you try to do all of this at once. I could go on for a very long time about what all of the different problems are, what the limitations are, but I just thought I would highlight a few of them. So one of them is that we have a very large separation of scales. If you're interested in the merger, that happens on the order of tens of milliseconds. If you're interested in the counterparts, that happens on the order of seconds to days. You can't model both of those at the same time. You just don't have the computational resources to do it. Furthermore, if you are interested in just like the structure of the magnetic field, the merger dynamics happen on the order of kilometers, tens of kilometers. We measure the gravitational waves, hundreds and thousands of kilometers away. But the actual magnetic fields themselves are subject to turbulent instabilities that happen on the order of a meter or so. And so you can't really resolve both of these at the same time with our current computational capabilities. And part of that is because we're bound by a curse of dimensionality. Even if you are one of the 3 people in the world that do SPH for neutron star simulations, you still have to model your gravitational field on a grid. And that means that if you wanted to double the resolution of your calculation, you have 3 dimensions that all get doubled, and that increases your computation by a factor of 8. And then you have to have your time steps remain stable, and that gets you that extra factor of 2 to make, doubling your accuracy 16 times more expensive. And then, as mentioned before, we have physics uncertainties, and this really affects the quality of your modeling. This means you need to run a very large parameter study for basically any phenomenon that you're interested in to really get an idea of whether or not what you're looking at is physical, or if it's just subject to, some nuclear theorist interpretation of the equation of state. And then finally, this is all before we even think about actual limitations in the numerical methods themselves. And so we have to introduce various approximations in order to solve some of these things, to make them tractable, or just to deal with certain terms in the equations. And these all introduce errors of their own. What this all adds up to is that we really need better models for doing for neutron stars, because the ones that we have right now are not good enough. This table here is just a kind of looking at the quality of different numerical relativity simulations that were done. This is from a paper from Rossella Gamba and her collaborators a few years ago. And what they found is that even looking forward to something like the 05 run for LVK, our current waveform models and the numerical relativity simulations informing those just might not be good enough, that they will be dominated by systematic uncertainties that will kind of pollute our parameter estimation of these systems and really kind of bias the physics that we interpret from these systems.
What is your meaning by the word model in this plot? That you need a better one?
Yeah, we need more. So it's several things. One is that we need better numerical relativity simulations, but then we use those simulations to inform like waveform models that we use to then create templates for LIGO, and so those models are mostly what I'm referring to, but there are other things as well, that kind of models that we build based on the simulations.
So it sounds like the kitchen sink approach to the problem is horrible and should not be tried. But I'm curious, if you're interested in one specific sector of all of the physics that you laid out, can you get away? Are there like Whittle algebra type estimates that you can make where, if I want to understand this physics, I need to do this part really carefully, but the others I can neglect? Or is it like the nightmare scenario where everything is really strongly coupled, everything talks to itself? Like your waveform is really affected by how you solve neutrinos, for example.
So that there is some good news in there, which is like if all you're interested in is like in spiral waveforms, the only thing you really need to model correctly is the fluid dynamics and the equation of state.
Mm-hmm.
You don't really need to worry about neutrinos until your post-merger. Nuclear burning doesn't happen till, long after. We usually don't even include that in our simulations as is. And even magnetic fields aren't super important during the spiral. But if you want to do any sort of post-merger effect, you kind of have this, you kind of need all of these things because they all contribute. And so, if you leave out some of these physics, you can really only make statements about particular things. They're not necessarily informative for actual gravitational wave modeling.
And can you like do this in sort of like stages? For example, you can run maybe the merger using the physics that matters, stop it, initialize a new simulation where all the new physics then kicks in and turns on, given some, what you had for what the space-time looked like after the merger, and do this iteratively.
Yes and no. You can do it with some of it, but for example, like magnetic fields, you don't just turn them on at the end, or you get it. Just the fields themselves, the field structure isn't correct. But you can do it with some other physics.
So given the physics uncertainties, are there scenarios where it doesn't make sense to increase the precision to reduce the grid size because we're dominated by physics uncertainties anyway.
So right now that is the case.
Yeah, so
But
only for some specific purposes, I suppose we actually need to have a more grid size. Only when we want to distinguish between two physics models, for example.
yeah, right now that is the case. But in a few years, that will not be the case.
Okay.
If I were up to date on the equation of state modeling in 2023, could you summarize how things have changed in the last 3 years? In the sense of, is it better or worse?
It's about the same.
Oh.
We have, things like nicer occasionally give us like new data points, new constraints, but really it's about the same. There have been no kind of significant changes saying these equations of state are no longer permissible. These ones are favored. And so there's still a pretty wide range of things that still work. Okay, so that was all just introductory material that I spent 15 minutes on unnecessarily. And so now I can actually tell you about some of the work that I've done. And I think a lot of you here have probably heard of AthenaK. A lot of you here use AthenaK. But I spent most of my PhD working on AthenaK, and so you get to hear about it some more. I spent most of my PhD, as I mentioned, working on code specifically so that we could do binary neutron star mergers. AthenaK is really nice because it uses this COCOS performance portability framework, which makes it so that we can write our code once in theory and then run on any architecture we want, including GPUs. And GPUs are really nice because they're very good at crunching numbers really quickly. And that makes them ideal for a lot of things, including their original applications in movies and video games to now they're also very useful for scientific computing, for AI, basically anything where you just need to crunch a bunch of numbers really, really quickly. Because it's descended from Athena++, it has a bunch of features that I won't go into detail on that make it give it some really favorable qualities that make it very computationally efficient, that make it work really well on large machines. To give you an idea of kind of the benefits that we're looking at here, this is a performance test, some performance tests that I ran for AthenaK in kind of a merger-like scenario, and then some other tests that I did as well. This plot on the left basically describes what's called weak efficiency. And so this is, or weak scaling efficiency. So you can think of this as you increase the number of resources that you use, you keep the problem size fixed per unit of resources. And really what this measures is how efficient is the communication in your code. Because as you add more processors, you need to communicate between them, and that adds overhead to the situation. What we find with AthenaK is that in a kind of merger-like scenario, it maintains better than 70% efficiency through more than 65,000 GPUs. So at the time of testing, this was done on Frontier, which was then the most powerful machine in the world. Basically saying we could do whatever the heck we wanted on any machine we could use. And then this table over here on the right kind of shows speedups that we see with AthenaK relative to various architectures. So this top row here is just kind of a CPU node on a typical supercomputer. And then these are just different processors, GPUs, CPUs that I tested it on. And with AthenaK, we see on our GPU architectures roughly an order of magnitude improvement for one GPU compared to one CPU socket. It turns out GPUs are so fast that on my laptop in my office, I was able to run very crappy, but still nonetheless, it worked. I was able to run merger simulations on them. And that was how I was able to test the code. And that's something that has, not really been practical before.
I guess, how do you not get killed by communication when scaling up to such a large number of GPUs? What's the secret sauce there?
So it's this, one is this octree AMR. So everything in the on the grid is kind of built into these little, separated into these little blocks that are sorted into an octree that keeps them very close together in memory. And that makes it so that, data that will have to be communicated frequently between blocks doesn't end up on separate processors. That's one thing that helps. The other thing that helps is that we use it's called task-based parallelism. And so if a particular GPU or CPU is working on a task and needs information from another neighbor, it can just move on to the next task that it doesn't need information for. And so you're able to kind of overlap communication with computation.
So in the plot of the weak scaling, so this might be like stochasticity or the error bar on each point. Is there a reason that one point just became larger than one?
Yeah, it's stochastic. Yeah. So
this is the error bar on each point. It's scale.
Yeah, there's a little bit of a scatter when you do these. It depends on a lot of things that are.
And do you know the reason why it starts to break at 1,000?
Not
That's just observation.
it's just, but yeah.
What are these two tests, TOV and turbulence?
Okay, so this TOV test is so the turbulence test is I just had like a uniform box that I was doing like I don't remember what I did exactly, but it was like a Kelvin Helmholtz instability in like a uniform box with just the GRMHD solver. And then the TOV test included a dynamical spacetime. This is just a static neutron star that with AMR that kind of resembles what you would see in like the post-merger phase of a neutron star merger.
These efficiency tests work so good also on realistic physics problem that you want to solve, not just Kelvin Helmholtz on a box and.
Yeah, I mean these tests were set up to kind of resemble problems that we would be doing. And so like this TOV test, again, it's a slightly idealized, but it's not very far removed from the actual problems that we do.
Run this turbulence test. Do you have AMR as well?
No, this is just on a uniform grid. So because AthenaK is very fast and scales very well on large machines, we've been able to get a lot of kind of novel science out of it. And so one of the applications that I've used it for was I looked at kind of flux emergence in binary neutron star mergers. So the idea is you have this very strong toroidal field in your post-merger remnant. And the question is, can that field break out and then contribute to magnetic outflows? Maybe, can you get some sort of relativistic jet that kind of it originates in some way from this field, or does it kind of stay trapped inside? Because of AthenaK, I was able to run pretty high resolution simulations of like localized simulations of little wedges of neutron stars looking at this effect with kind of an idealized model for the field. And they were almost inconsequentially expensive. Like we're talking, 1 or 2 days on 2 nodes. And kind of the end result after doing a bunch of these simulations is the conclusion is that most likely what you need in your remnant, if you want to get some sort of flux emergence, sort of similar to like the way that we have coronal mass ejections and solar flares in the sun, is you need a very strong magnetic field because the remnant is stubbornly stable against all of the instabilities that you would like that kind of help propel magnetic fields effectively. And so this plot here is just kind of a simulation or plots of one of the simulations I did that did get breakout. So you can see this little flux tube that expands and then eventually breaks out of the neutron star. More recently, another application that was very exciting was because of AthenaK and its amazing scaling ability, we were able to do very high resolution simulations of Kelvin-Helmholtz instability in a post-merger remnant, looking at kind of the shear layer that forms as the 2 stars collide against one another. And we were able to find conclusive evidence of a turbulent dynamo operating in the post-merger. And basically the idea here is that you have all this, the Kelvin-Helmholtz instability seeds all of this turbulence that generates these small scale vortices that amplify the magnetic field. But then because of this dynamo, there's kind of this inverse cascade back up that creates large scale structure that would be important possibly for contributing to magnetic outflows and other things.
So you mentioned at the beginning that there are a few problems to study, not just mergers. One of them was physical uncertainties and large separation, scale separation. And then you said, okay, we have a code that is very, very efficient. Mm-hmm. And look at this, I can do science. I've managed to overcome the problems, but only computational efficiency cannot overcome whatever physical uncertainty that you have. So how much is this science dependent on some uncertainties that you have?
Yeah, this particular effect is not subject to uncertainties. This is just basic fluid dynamics. This is something that will, the conditions are fairly universal regardless of the equation of state that you use. Really, the only thing that would change here is how big is your merger? Does it immediately collapse or something?
And the separation scale of the instabilities of the magnetic field and the emergence of the whatever signal that you have, was that overcome by the efficiency of the code, by MR?
This still is not high enough. We are still subject to kind of this separation of scales. And that's actually why we started with a merger simulation and then we did local box simulations of the actual instability, because there still is this separation of scale issue. But one of the things that I'm getting to is that even these local simulations would have been impossible without the code. Because we needed, order 10 million GPU hours to do these simulations.
By what factor do you amplify the material field?
In these simulations, it was, I want to say 4-ish orders of magnitude. We started somewhere around 10 to the 12 and we ended up with fields order 10 to the 16.
Does this change anything about the interpretation of the binary neutron star that we do have?
In terms of the physics that's already well established, not necessarily. What it does kind of, one of the things that it does kind of help us understand better is the process for generating very large magnetic fields, because we can't resolve there's a very strong amplification that happens, as I mentioned for Udipan's question. We kind of start with what typically happens in a merger simulation is we start with an unrealistically large magnetic field, knowing that we can't resolve the actual amplification. And so what this could be used to do, for example, is calibrate some sort of subgrid model or something like that would allow us to start maybe with a more realistic field, but then just have some, some sort of little source term that helps amplify the field when the physical conditions are correct. Does that kind of answer your question?
You said you start with 10 to the 12 dots. Where do you get that number from?
That's kind of toward the upper end of what we see in like isolated neutron stars that would kind of be progenitors for these systems.
So the surface modeling.
Yeah, this is 10 to 12 in the center, and so it was closer to maybe kind of a 10-ish on around the surface. And so then this is a science project that I am not actually actively involved in, but I talked with kind of the people who are working on it because it's a kind of a really great example of what we can do with AthenaK. They're very interested in doing prompt collapse. As I mentioned, these are these very large neutron stars immediately collapse into a black hole at merger. And what they specifically want to find is kind of the critical point where this happens, this kind of threshold mass for the system that leads to critical collapse. And because you have a large parameter space, this means you need to do a lot of simulations to kind of understand exactly what's going on and see if there are any kind of features that are independent of things like the equation of state or can be generalized in some sense around the equation of state. But the kind of crux of what I'm getting to is they were been able to perform over 200 simulations at a cost of about 250,000 GPU hours. If you convert that to like the CPU hours on their same machine, we're talking about 2 million. To put this in perspective, my very first simulation project during my PhD, I used 500,000 CPU hours to do 6 absolute garbage simulations. And they had been able to do more than 200 with not much more, computationally speaking.
When you do a parameter study of this kind of physical scenario, are the output diagnostics that you use to try to infer things from the simulation smooth in the input parameters at all, or is it just things jump around wildly and there's no clear correlation? Just depends on the diagnostic.
It depends on the diagnostic. The usual one here is just, did it collapse or not?
Mm-hmm.
And that tends to be fairly monotonic with something, for example, like the mass of the system.
Mm-hmm.
So, you're talking about, in response to Gary's question, maybe using some classes of simulations to develop subgrid models. So broadly, like schematically, how does this field work in the sense of one approach is just do scattershot, do a whole bunch of simulations and try to directly match simulations in some way to observations, et cetera. Another is to try and develop some theoretical understanding of, in the black hole image case, if it's brighter here, that tells us something about the spin of the black hole. So
in terms of like where we usually use subgrid models is for magnetic field turbulence. And so really what you need is what will happen is you'll typically have some sort of quasi theoretical model. Usually it's still kind of phenomenological in nature, but there are some like, theoretically driven aspects of the model, and there will be some tunable parameters, and you can take even just like one really high quality simulation and kind of measure what that parameter looks like at various points, and then use that to kind of calibrate the model.
But outside of the magnetic fields question, is it more that you know what the answer is and you're finding the prefactor, or is it that you have no idea what the answer is?
For a lot of emits, we have no idea what the answer is. Like there are a large set of what we call quasi-universal relations that we have observed. There just seems to be some sort of trend between, two different quantities. And we just kind of fit some law to it and say, oh, look, it works. And some of them are actually pretty robust, and then some of them are, not, they need a little bit of work. Yeah. So the next thing I'll talk about is what are called not quite transcendental functions. So what I've talked about with AthenaK is basically just figuring out ways to brute force our problems harder. But another aspect of good kind of computational physics is finding ways to do the same problem, but with better algorithms that either make it faster or more accurate. And in this case, this is what I'm going to be talking about is a trick for making things a little bit faster. This is all about work that I did with Peter Hammond, a collaborator of mine who's now at the Albert Einstein Institute. So a little bit of background. I've referenced these nuclear equations of state that we use. They most decidedly are not ideal gases, seen here by the scaling law between the pressure and the mass density. These nuclear interactions are very computationally involved, and so we can't do them in situ in our simulations. And what that means is that we just make these big giant tables of all of the quantities we're interested in, and then we just interpolate them on the fly. And because we have to cover several orders of magnitude for things like density, things like temperature, we logarithmically scale them. Logs and exponents are very expensive. And if we're interpolating things that are logarithmically scaled, we have to make lots of log and exponent calls. And we found that the speed up of the slowdown of putting tables in AthenaK was particularly bad compared to putting them in a CPU-based code. And so Peter and I thought a lot about, how do we kind of make this faster? How do we, make it so that we actually retain some of these benefits from moving to a faster code?
The GPUs compute logs worse than CPUs?
I think what a lot of it has to do is that you're very bandwidth constrained on a GPU, like memory bandwidth. And a little dirty secret that not everybody necessarily tells you is that some of these operations, division is another operation where this is the case. They require more registers than it appears when you do this calculation. And so you create a lot of register pressure when you perform these calculations. And that really strains your memory bandwidth.
Is this solved by like H200s, which have 140 gigs of VRAM?
No. They have a lot of VRAM, but it's the actual bandwidth that matters. And that's just one aspect. There are also the operations themselves are just a little bit expensive because they're transcendental functions.
Then that's the physical wire connection between the registers and the compute and then the on-device memory. It's just that is too small, and so you have to keep shunting back and forth. I mean, because I don't understand the register pressures with respect to the memory.
Yeah, I mean yeah. So this is if it can't fit it in the registers, it has to shove it in the main memory. So I will back up for a minute and talk about something a little bit technical, just to kind of motivate the solution to the problem. So floating point numbers are, how we typically represent decimal numbers on a computer. So you'll have some, number of bits, and a particular region of those bits will be allocated to the mantissa, the significand of your number. And then another section will be, saved for the exponent. And you can represent all of your floating point numbers as m times 2 to this exponent. You'll notice that, just doing a little bit of elementary math, if we take a logarithm of this floating point number, it's just going to be the power plus the logarithm of the mantissa. You'll notice, we already know what the exponent is. That is stored explicitly in our number. And so we don't need to calculate this. We can just pull it straight out of the floating point representation. Really, the only thing that you need to calculate is this mantissa. Maybe we can be clever. Maybe we're working really, a little bit too hard, and we can only worry about this mantissa term. And this was kind of what motivated a cool idea called not quite transcendental functions that a group at Los Alamos had a few years ago, where they observed that when you are working with things that are scaled logarithmically, often what you want isn't necessarily for it to be logarithmic. What you want really is that you have some function that maps a very large dynamical range to a few evenly spaced points. So this log-like scaling property is a lot more important than actually being logarithmic. Now, the problem is the Los Alamos group's idea didn't actually work. It's a little bit of a long story, but it turns out that if you try to use it, it generates a lot of noise and artifacts in your simulation. It's not really useful. But effectively what they came up with was this very clever idea of just basically doing like a piecewise interpolation of a logarithm that ends up being exactly invertible. So as Peter and I were kind of working on this, he came up with the idea, well, maybe we just, rather doing piecewise linear, what if we just do piecewise quadratic? And so you end up with a fairly simple approximation, piecewise quadratic approximation to a logarithm and an exponent that can be done with a few arithmetic operations and a single square root, which turns out is still cheaper than doing a logarithm or an exponent.
Sorry, Jacob. So the idea is that the square root is sufficient compression of the dynamic range of the numbers that you're trying to solve compared to the logarithm?
Well, no, the square root pops up because of because you're trying to invert the quadratic equation.
Okay. Because they were doing something piecewise linear before. So
yeah. We implemented this into AthenaK. We used what are known as bit hacks, basically just manipulating the floating point representation to get really results. And what we found is that putting these in the code, we got a global speed up for a numerical relativity simulation on every architecture, and sometimes it was as much as 30%. And to clarify, this is not the tables themselves are 30% faster. It's the entire simulation is 30% faster.
Are bit hacks part of the compiler contract? All cases?
So the way we have them implemented right now is technically not compliant with standards. Like there is some technical undefined behavior in there, but there is a way to do it that is completely within compiler standards. We just have been too lazy to go fix it because it hasn't broken yet.
Are you using it only in the table interpolation or everywhere else?
We use it in the table interpolation only.
Let's see, basically do a second order Taylor expansion of law.
No, it's not a Taylor expansion. It's a piecewise quadratic. So it's like, you know what your logarithm has to be at powers of 2. And so you have these fixed control points. And then you just, rather than solving the actual logarithm in between, you just have some, quadratic fit to those.
It's spline.
Yeah, it's like a spline, but it's quadratic instead of cubic.
What happened to computers or numerical methods or whatever that this problem became some dominant over others, that this solution was only found now. I mean, evaluating tabulated physical information of whatever EOS as opacities, nuclear cross sections,
So-
whatever, is like decades.
I mean, so these kinds of ideas are not, basically, the kindest way I can put it is that scientists are really terrible programmers,
You don't say.
is what it really comes down to. Because like tricks like these have been used in, like applied mathematics, gaming industry, basically anybody that does a lot of number crunching, like these kinds of tricks are actually very common. It's just scientists are notoriously terrible programmers. And so we don't ever really think about it at this level.
Yeah, but how come problem of logarithmically spaced tables wasn't dominant in the past? Because it was implemented in codes. There probably was something that was much more expensive than this. So
I mean, so we noticed it was particularly bad on GPUs. Like typically the slowdown on CPUs was, if you implemented it correctly, was order 20%. And other people's implementations are much slower than that because they're dominated by things other than these. It's just in our implementation, we had done it as kind of efficiently as you could with the way it would, for a logarithmic table. And this ended up being the bottleneck that we found.
You could do the same for exponential and other transcendental.
Yeah, so we as part of this, we have an approximation to an exponent as well. Because you need to be able to invert it.
Let's talk about the approximants. So those are like Taylor series, but with rational functions. So like they're usually useless when you actually want to expand something, but they involve less arithmetic operations and they don't have square roots.
So,
So maybe they're possibly, I don't know, possibly faster.
yeah, I mean, it'd be interesting to think about. I don't know for us that it would actually be that helpful because what we really need is we need something that is C1 at these control points. And I'm sure you can construct something like that, but whether or not it actually ends up being simpler, I think
It might
is.
not be invertible, right? It's just a ratio of rational functions.
The thing is, you only need it in a certain short interval, so I think it can be invertible within that interval, right? Between 0.5 and 1.
Yeah, I mean,
The argument
yeah, as long as like, yeah, I mean, it would be something I could think about.
But is the goal there would be to increase accuracy, not to increase.
increased accuracy or also remove that square root, which presumably is a bit slow to calculate every time, right? Like on that operation, so surely the square root is the bottleneck of.
Yeah, I mean,
Yeah.
this is substantially more expensive
So
than.
if you have only rational functions, maybe I don't know, just maybe.
Anyway, so one of the, I need to speed up a little bit. One of the questions that you might have is, because we've scaled this slightly differently, we have to some degree, slightly modified what our table looks like. And that means we have changed the equation of state. And what does that do to our binary neutron star waveforms? Because they are sensitive to the equation of state. And it turns out that for a reasonable, a table with a reasonable number of points in it, the NQT functions are sufficiently accurate that get something that's the difference between whether it's scaled logarithmically or with NQTs is smaller than just changing the resolution in your simulation. Or it's to the uncertainties in the equations of state themselves, they are effectively identical.
Your third bullet point here. That's important.
Yes. So there is a very small shift in the merger time because you've changed the equation of state very slightly.
I see.
But just increasing the resolution produces a bigger shift. And so this is a subdominant effect.
Does the shift become larger at higher resolutions?
I have not actually checked that. I would assume that it would be similar because the equation of state would be the same. But
What's the golden standard for aligners like a library. The waveforms, like how much of this delta file of phi is acceptable?
Kind of the state of the art are like subradian in accuracy, which we can achieve that with AthenaK. We have subradian accuracy. I did some simulations with these. Basically, the science application here is that it does make the code significantly faster, and so we can do reasonably accurate BNS runs using these NQT functions at a much lower cost. And so I was able to push down to 92 meters, which is about twice as fine as it's considered kind of the standard BNS simulation these days, and got phase errors that are about 0.1 radians over 7 orbits. And they were relatively affordable for about, these runs were about 50 milliseconds long. The low resolution ones finished in a couple days. The medium resolution one finished about 3 or 4, and then the high resolution one took about a week.
How does the error in the NQT compare to the uncertainty in the EOS? Supposing you fix an EOS model.
So for a reasonably spaced table, so a reasonable number of points, it's significantly smaller than the actual uncertainty in the original state.
You specifically want to avoid having cusps, so it doesn't introduce the artifacts, and once you have that, then effectively you're good.
Yeah. So the last thing that I'll talk about, and I'll kind of move through this quickly, is I've also been working on adding a new HLLD Riemann solver to AthenaK for GRMHD. And specifically, this is not, that part is not novel, but what I've been focusing on doing is trying to make it computationally efficient. Just to give a little bit of background, when you solve a conservation laws can be nonlinear or are often nonlinear, and so they can produce shocks and discontinuities in your solution. And regular numerical methods break down at these discontinuities. And so a model problem for how you handle these discontinuities is what's known as the Riemann problem. You can think of, you have 2 constant states that are separated by a single discontinuity. And then using the kind of features of your conservation law, you can do some sort of characteristic decomposition to create what's called a Riemann fan, where you look at all of the ways that all of the different waves in the solution and how they propagate through time and space. And then based on kind of the speed of your discontinuity and how it relates to these waves, you can figure out kind of what the state should look like, and then use that to compute the flex. And these are kind of the building blocks for all of the numerical methods that we use. The standard approach that's used in GRMHD, because GRMHD is hard, is a 2-wave solver based on what's called HLLE or HLL, just acronym for the solvers, the names of the architects in this method. Basically, what you do is you only consider the extremal wave speeds, and then you just average over all of the interior structure here. And then by enforcing jump conditions, you can compute what this intermediate state should be, and you have solved your Riemann problem approximately. Okay, thank you. This is cheap, it's robust, and it is also very diffusive because it smears out everything but the fast shocks that are represented by these waves. HLLD is a method that has been used in Newtonian MHD for a very long time that restores some of the interior structure. The relativistic version is a little bit tricky. It can only be solved iteratively, and then you have to do some sort of tetrad transformation to use it in GR, because we only know how to do it in flat space. All of the technology to do this exists. This is not novel. One of the big challenges, and where I've kind of done my little innovation here, is in how you initialize this iterative method. The original initial guess for the relativistic version is very expensive. It requires what's known as a conservative primitive inversion, which in Newtonian MHD is very cheap. It's very easy to do. In relativistic MHD, it is basically everybody's worst nightmare. And so doing this for an initial guess is kind of, it seems excessive. And it becomes prohibitively expensive when you're using it with something like a nuclear equation of state. It turns out you can actually do a much simpler initial guess. It is basically a weighted average, and it avoids the primitive inversion. There's no obvious loss in accuracy, and it reduces the cost so much that a full merger calculation with HLLD is only 5% more expensive than doing it with HLLE. So I have some preliminary results that
What was the cost before this innovation?
it was usually in excess of 30%, sometimes more. In some circumstances, it could effectively double the cost of the simulation. So the method works. It has been implemented in AthenaK, but I'm still doing kind of tests to see what all of the effects are. There is some small evidence that is still being explored. This is all very, very preliminary. That you get stronger magnetic outflows, which kind of makes sense because you're able to resolve these the interior structure of your Riemann fan a little bit better. You're going to have sharper features, less diffusion. You should be able to get more, magnetic field amplification, those kinds of things. But one thing that is interesting that we see as well is that there's some evidence that the waveforms themselves are a little bit less diffusive. One of the ways that diffusion manifests itself in a BNS waveform is that it tends to cause neutron stars to merge a little bit sooner. It effectively increases the tidal deformability and will therefore decrease the merger time. And so what we see with HLLD is that it seems that the merger time is being shifted to the right a little bit, which is some evidence that it's decreasing the diffusion in our mergers and giving us more accurate waveforms.
There was no comparison between HLE and HLLD before this.
There is another paper that does a comparison in the context of mergers. They don't really look at the waveforms very in great detail. They look at some other things much more.
This is because it was too expensive before your trick, or just that's what it is.
No, they just didn't compare them. Like this is a group that the other group that has done this. Computational expense literally doesn't matter to them. They have like their own private allocation on one of the biggest machines in the world, and so they literally just throw whatever they want into their code and can do it. But for some reason, they just didn't do this comparison. So there are a few possible applications that we're thinking about. Obviously, we can get more accurate in spiral waveforms, but also we're thinking about maybe we can do a more accurate studies of tidal mode oscillations. Something that I'm working on at the moment is that HLLD is kind of a necessary stepping stone because of some numerical properties that it has, or mathematical properties that it has for building some more advanced numerical methods that would be very novel and would improve things substantially if they work out. But this is all, just kind of things that we're thinking about at the moment. But I'll just leave you with my summary. I realized I didn't have any nice videos for you, and so here is one for you. Thank you very much for your attention.
We're doing a lot of discussion already, but maybe we have time for one or two more questions for Jacob and do Udapana session.
So in your Riemann fan, you need all the wave speeds, right? First have to compute using linear perturbation theory, whatever, what kind of waves you have in the system. So the fastest and the slowest are the fast and slow magnetosonic modes, and then you have the alpine mode in between. But I see more there. So,
Yeah. So in full MHD, you have 7 waves. You have fast and slow magnetosonic waves. You have an entropy wave, and then you have your outfade waves. Yeah, and this entropy wave is associated with contact discontinuities.
What's the metric weight?
Hmm?
What's the phase velocity metric weight?
It
This moves with the flow, doesn't it?
it moves with the flow, but you have to calculate it becomes a little bit subtle when you have in the actual context of a Riemann problem because you have different flow streams on the left side.
Yeah, these been calculated for GR and HT properly.
Technically, yes. They're horrible. So your magnetosonic waves are the roots of a quartic equation. And so typically we actually just use a biquadratic approximation to get these extremal speeds.
I looked like you maybe had a question.
Yeah, so what is the better guess again? Like, how do you guess better?
So the long story short is that it's a weighted average of the pressures between the left and right states. How I arrived at that is a very long story. But it turns out that it works remarkably well. And
Can it be used for situations where there is no GR, like any other solver before this?
I mean, the method that how I kind of arrived at it is a fairly general technique. And so in principle, yes, I don't think you actually need it. In Newtonian physics, HLLD has a closed form solution. You don't need to do it iteratively.
Oh, I see.
Right. Maybe we can continue the discussion at lunch. Let's thank Jacob one more time.